Hey everyone, and welcome to this explainer on software processes, covering Chapter 2 of our textbook. I am really glad you're joining us today. Writing code is actually relatively easy. Basically, anyone can sit down and write a quick little script. But building reliable, large-scale software systems that don't crash when thousands of people try to use them at once, that is incredibly hard. And that is exactly why we need software processes. Today, we're going to explore the precise, structured methods that professional engineers use to turn an abstract idea into a robust, working system. All right, let's take a quick look at today's syllabus. We're going on a structured journey through the text. We'll hit software process models, process activities, coping with system change, software process improvement, and finally, a summary and exam prep. So, let's start right at the foundation. What exactly is a software process? Well, by definition, it's a coherent set of related activities that leads to the production of a software system. Now, here's the thing. There is no single magical universal method that works for every single project. The process a company chooses depends entirely on what kind of software they're building, what the customer actually needs, and, frankly, the skills of the development team. But whenever we look at a process, we're always looking at three specific things. We look at the products or deliverables, like architectural models. We look at the roles, like project manager or programmer. And we look at the pre- and post conditions, which are basically the rules that absolutely must be true before and after a specific activity happens. Now, even though there are tons of different processes out there, every single one of them has to include some version of these four fundamental activities. First up is software specification. This is where we define exactly what the system should do and what its operational constraints are. Second is software development. That's the actual designing and programming of the software. Third, we have software validation. This is where we check to make sure the software actually does what the customer wants it to do. And fourth is software evolution, which is modifying the software over time to meet changing customer needs. So whether you end up working for a tiny 3-person startup or a massive global corporation, you are absolutely going to be doing these four things. Okay, moving right along, let's dive into Section 2.1, Software Process Models. You can think of a process model as sort of a simplified blueprint that organizes all those activities we just talked about. The very first model we need to discuss is the classic waterfall model. This is a plan-driven process where the fundamental activities are represented as strictly separate sequential phases. It's literally like water cascading down a series of steps. You specify, then you design, then you build, then you test. Now, I want to pause here because there's this really common misconception among students that waterfall is a dead methodology. That is simply not true. While it's true that it requires a lot of early commitment and makes going back to fix things pretty difficult, it is absolutely crucial for safety-critical systems. It's also necessary for massive systems engineered by multiple partner companies, where you literally need a complete, locked-in specification before anyone writes a single line of code. So the big concept to grasp here is the difference between a plan-driven approach and an interleaved approach. In a plan-driven process, like Waterfall, you plan and schedule all your activities completely before you even start development. It is rigid, upfront planning. On the flip side, we have incremental development. Here, specification, development, and validation are all interleaved. They happen together. You build a quick initial version, you get rapid feedback from the users, and then you evolve the software through several continuous versions. This really highlights how we decide which model to use in the real world. Real-world engineering is all about picking the right tool for the job. Waterfall is your go-to for those safety-critical or large-scale partner systems. Incremental development, that is the gold standard for business systems, e-commerce, and mobile apps, where the requirements are changing all the time. But we also have a third model to consider, integration and configuration. This one relies heavily on reusing existing components like standalone applications or web services and knitting them together using frameworks like Java Spring. You aren't building everything from scratch, you're configuring and connecting pieces that already work. All right, let's transition over to Section 2.2, Process Activities. So we just covered our three main blueprints: waterfall, incremental, and integration. But what do developers actually do all day within these models? Well, it all kicks off with requirements engineering. This is the crucial process of understanding and defining what services are actually required from the system and identifying the constraints on how it operates. I really want you to pay attention here because this is a make or break stage. Mistakes made during requirements engineering will cascade catastrophically into the later design and implementation phases. Think about it. If you build the wrong thing entirely, it doesn't matter how beautiful or bug-free your code is. Let's break down how this process actually flows. We start with requirements elicitation and analysis. This basically means talking to stakeholders to figure out what they actually need. That raw information then feeds into requirements specification, where we translate those loose needs into formal user and system requirements. Next, those move into requirements validation, where we rigorously check them to make sure they are realistic and consistent. And notice the feedback loops here. When we find errors during validation, and we have to loop back and fix the specification. The final output of this entire cycle is an agreed-upon, finalized requirements document.
Okay, so fast forward a bit. Once we've actually built the software based on those requirements, we hit validation, which is very often called verification and validation, or V&V. This is the process intended to prove that a system not only conforms to its specification, but also meets the true, real-world expectations of the customer. Now, while this does involve activities like code inspections and design reviews, the vast majority of your time and effort in V&V is spent on program testing. That means actually executing the system with simulated data to hunt down and fix errors.
This brings us to a really elegant concept called the V model of development. This maps out exactly how testing works in a plan-driven process. Imagine a large V. As you move down the left side of that V, going from requirements specification all the way down to detailed component design, you aren't just designing the system. You are simultaneously dictating specific test plans that sit on the right side of the V. For example, your system specification directly informs your system integration test plan. When the component is finally coded down at the very bottom point of the V, you then move up the right side, executing those tests in order. It's a brilliant way to tightly link your development decisions directly to your testing strategies. But hey, here's a question to wake everyone up. We've talked a whole lot about strict plans and locked-in specifications, but what happens when the business environment suddenly shifts or brand new technology emerges? How do we actually cope when requirements inevitably change halfway through our beautifully constructed plan? That brings us right into section 2.3, coping with change. The harsh reality of software engineering is that businesses and technologies change constantly, and change adds massive rework costs, which means spending money to redo work that was already considered finished. To handle this, we rely on two primary strategies. The first is change anticipation. This means deliberately building activities into your process that help you predict possible changes early on, way before you've spent millions of dollars writing code. The second strategy is change tolerance. This is where you architect the process and the software itself so that changes can be easily absorbed later. This is normally done by using incremental development, where if a change happens, you just alter an upcoming single increment rather than tearing down the whole system. A really perfect example of change anticipation is system prototyping. A prototype is basically a quick, early, bare-bones version of the system. You establish your core objectives, define the basic functionality, develop it rapidly, and then, crucially, you let the users evaluate it. By letting users get their hands on a prototype first, they can refine their requirements early on. They might realize they actually hate a feature they thought they wanted. This anticipates and resolves change before the heavy, expensive final software production even begins. Now, over the lifespan of a system, change never really stops. A really common misconception is that there's a hard, concrete line between software development and software maintenance. But in reality, that distinction is becoming increasingly irrelevant. When we look at how a system evolves, we see that you define requirements, build the system, assess it, propose changes, and then modify it in a continuous, endless loop. Software engineering is truly an evolutionary process that lasts throughout the system's entire lifetime. Let's wrap up the main concepts with section 2.4, process improvement. So we know we can use prototypes and iterative delivery to cope with constant change. But how do the development companies themselves get better at doing all of this? Well, the overarching goal of process improvement is to enhance software quality, reduce development costs, and accelerate delivery schedules. Software companies are under immense, constant pressure to deliver cheaper, better software on incredibly tight deadlines. To survive in that environment, they have to constantly analyze, measure, and upgrade their own internal software development processes. It's all about looking critically at how you build software and finding concrete ways to build it better the next time around. All right, Section 5, Summary and Exam Prep. Let's get into the key takeaways. If you haven't been taking notes, now is absolutely the time to start. Let's methodically lock in these key facts.
First, remember that a software process is the set of activities leading to software production. You definitely need to know the fundamental differences between the waterfall, incremental, and integration models. Never forget the 4 universal activities: specification, development, validation, and evolution. Remember that requirements engineering is hypercritical because it dictates your system constraints, and early errors there are wildly expensive. Know the V model inside and out, specifically how it links your left side development stages directly to your right side test plans. And finally, remember that we manage the inevitability of change via prototyping and incremental delivery. Grasping all of this sets us up perfectly for Chapter 3, where we are going to dive deep into Agile software development. Before we go, I want to leave you with a somewhat provocative thought to chew on. Based on everything we've covered today about evolution and constant change, if software must constantly evolve to remain useful in a fast-paced, changing world, is a large-scale system ever truly finished? I highly encourage you to ponder the continuous nature of software engineering as you review your notes this week. Thank you so much for attending this explainer. Keep studying these models, and I will see you in the next one.